and turn off this one. So. Okay, so yeah, welcome to the 8th lecture today, and actually we will have 3 lectures more, maybe 3.5 perhaps, on now everything on stability. I will afterwards give you a short outline of what we're going to talk about, but in some sense I think it's kind of the most interesting bit of this talk or of this presentation or of this lecture, but maybe also the most complicated part, because there's quite some math that we need to look at. It's not very difficult math, but everything is kind of on a, you need to know a little bit about derivatives and so on to understand. But whenever there's anything unclear, I'm happy to, of course, provide more details if needed. But as usual, I would just like to summarize very briefly what we did yesterday. If you remember, we looked at the Faulkner-Scan equations, or the family of similarity solutions. And I guess most of the time we actually spent on defining the conditions that are necessary for a Faulkner-Scan solution to be a valid similarity solution. And kind of on the way, we realized that the family for Faulkner-Scan is obtained when we have the parameters A, beta, and M to be in a specific way. So A here, that's the exponent that we use in the actual similarity variable, which we then have also seen that this A is relevant if we want to look at the streamwise development, for instance, of the boundary layer thickness. The beta here, that's of course related to A. The beta is the opening angle in a slightly specific way. So pi times beta h is the actual angle. If you consider the flow as being the flow over a wedge, so therefore these Faulkner-Scan solutions are also wedge flow solutions. And the coefficient m, which is again related to beta and a, is the exponent of the velocity field that you would look at. And of course here, if you write it in this way, you directly see that this m essentially describes the pressure gradient that you would have in this case, because a variation of u via the Bernoulli equation gives you a variation of the pressure. But A, beta, and M are just different ways of expressing the same thing. They're all related with each other. They're not independent. But anyway, if we then have defined A, beta, and M, we can then come up with a modified Blasius equation, which is then the Faulkner-Scan equation, where we have this additional part here, which corresponds to the generalization when we even allow this pressure gradient to be non-zero. Again, just to remember, if the pressure gradient is 0, then beta h is 0. And of course, then this term would disappear, and we would just have the normal Blasius equations to solve. But in the case of pressure gradients, we have this additional term. And then if you want to get a velocity profile in a boundary layer, to get the boundary layer profile, we need to solve this whole equation for f, subject to these boundary conditions that are written here, and then we can, using the similarity variable, we can then go back to the u and the v velocities and have essentially the full boundary layer velocity. So that's the whole idea of what we did last time. And then of course at the end we have then realized that there is of course an APG situation and an FPG situation. APG meaning adverse pressure gradient, where we have the velocity decreasing, so we have a decelerating boundary layer. That's typically on an airfoil, for instance. I'll just draw an airfoil again. Here you would have here you would have an APG situation, of course, meaning that if you increase the angle of attack more and more, at some point the APG would be so strong that you would even get separation. And here in the front, typically would have an FPG situation, or also on the lower side of the wing, depending a little bit on the angle of attack. And APG, as I just said, they're prone to separation, meaning that the velocity close to the wall is lower, typically. So it means there's less momentum there, and therefore also separation is possible, because separation essentially just means that you don't have enough momentum close to the wall for the flow to be overcome the pressure gradient, and therefore the flow going forward. In the FPG situation, you have more momentum close to the wall, leading, of course, to more friction, as we also discussed. And the last important thing is this shape factor that we have also introduced. Yeah?
What's the meaning of F in FPG?
Favorable.
Favorable.
Favorable, yes. So this is adverse pressure gradient. And this would be favorable pressure. So FPG and APG, that's kind of, you know, standard words or standard abbreviations that we use. So the last thing I wanted to mention is this shape factor, the H, which is the ratio between the displacement thickness and the momentum loss thickness. And what I said last time is that this H is a good measure for the fullness of the profile. And what I mean with fullness is essentially what I try to indicate here with the red line. So in the case of a full velocity profile, it means that the velocity profile is very close to the wall. So it's you have a high gradient close to the wall, such that a lot of momentum is in the near wall region. And a thin boundary layer would be in the APG situation when you have a low gradient close to the wall and most of the momentum is actually further away from the wall. That would be a thin boundary layer. And the H, the shape factor, is now kind of a measure for that. And so if you have a full profile, your H would be low, and if you have a thin profile, H would be high. But as I said also last time, that's maybe important to remember, in the case of a velocity profile that's just constant right down to the wall, something that you would maybe get at infinite Reynolds numbers when the viscosity is extremely low, that would then have a shape factor of 1. So shape factor of 1 is really the minimum you can have. Okay? Yeah, this essentially is what we looked at last time. And then we also looked at some of the slides about stability, but we haven't really started with the theory yet. So that's what if you don't have any more questions related to boundary layers, then I would like to start with stability. Okay? Okay, so that would be kind of part number 2 of this lecture, and that would be hydrodynamic instabilities. Hydrodynamic instabilities. I don't really like the title of hydrodynamic because in the end we're not really limited to hydrodynamics. So I'd rather say it's kind of stability and transition. That's what we're going to talk about. So just to put everything that we do in this course into perspective, I'd just like to draw again this friction diagram that we have already looked at a few times. So we have CF, and the Reynolds number here, for instance, and it doesn't really matter what flow case we look at, but if we look at a pipe flow, for instance, we have, or we can take a boundary layer. We have something which is in the laminar case, where the friction goes down as Reynolds to the -1/2, which we have talked about. And then we have this turbulent correlation when Reynolds is on a different correlation, maybe Reynolds to -1 divided by 5, so minus 0.2 or something. And then we know that the real friction that you have for low Reynolds numbers, it would follow very, very closely this the laminar correlation, and at some point it will kind of go up and would then start to follow the turbulent correlation. So that means in this region we would call the flow to be laminar. In this intermediate region we would call the flow to be transitional, So transition between laminar and turbulent, and then of course in this region the flow would be turbulent. So in some sense, these three different parts are also the three different parts of our course. What we have done in part number 1 was to look at the laminar flow. So that was everything about the Poisson profile, Couette flow, was all the vorticity stuff, and also all the boundary layers were kind of in this first part in the laminar part. Ramis, starting next week, he will be looking at with you at the turbulent part. So in that part of the course, everything will be assumed to be fully turbulent. So everything has to be done with a statistical approach. So at that time, you will be talking about mean flows, fluctuations, RMS values, and so on. But what we're now going to look at is this intermediate part, part number 2, on these instabilities or transition in the flow. And of course, also here it's important to understand that if we talk about stability, it would be kind of this initial part when the friction is just about to depart from the laminar correlations. That's what we would call stability or instability. And as soon as the instabilities have grown sufficiently much so that we actually see a difference in the friction, then we would call the flow to be transitional. So I guess that's also an important distinction. Stability is really just here at the onset of transition, and then everything that has to do with predicting, the friction in this intermediate region, that would then be, it's not really stability anymore, but more in the realm of transition. Okay, so examples that we have now looked at where stability and transition, of course, are important are jets and plumes. We have looked at that very, very briefly last time or yesterday on some of the videos. Plumes, for instance, this was this, the Rayleigh-Benard convection when you had these convection cells building up. Boundary layers, of course, jets and plumes, boundary layers. There the example was, for instance, if you look at airfoils or cars, well, of course, it's important to know whether you have a turbulent flow or not, because that would, for instance, influence whether we have separation or not. And then we also looked at some examples yesterday on mixing layers. The example would be the Kelvin-Helmholtz instability. I remember this guy with this, this channel that he was tilting, and then you got the Kelvin-Helmholtz instability. So this would be Kelvin-Helmholtz, or also the clouds that we looked at, boundary layers. Yeah, I mentioned the airfoils, but of course the pipe flow by Reynolds was also a boundary layer flow. I guess one thing that is important to realize that the whole study of transition or stability and transition is actually it's a very complicated field. And as I was saying in the beginning, also very complicated, not just from the various physical aspects, but also from the mathematical treatment, the various tools that you can use from mathematics to predict the stability of flows. So I would say it's complicated both physically, but also mathematically. So that, of course, means that here in this course, we have 6 hours to talk about stability, and we can only scratch on the surface of what is actually possible in terms of studying these types of flows. But I still think it's important that I also give you a little bit the flavor of the mathematics behind it, and not just show you nice pictures, because I think it's actually, it's so interesting that hopefully some of you actually find this an interesting topic to study further and actually go more into depth of that. So here only the basics. Basics can be discussed. So the basics in terms of the math, but also in terms of the idea, the ideas behind it. And I guess we can summarize what we're going to talk about in two categories. So the first one is a specific flow stable or not? So that's the kind of the first question that we would like to look at. And then in the end, we will look a little bit also at the influence of noise on the whole problem. So what would change if we have a little bit of kind of ambient noise in our system? Okay. So if you now directly jump into stability and transition, I guess the main basic idea, and that kind of relates to the first question that I had here, is a specific flow stable or not? So the basic idea here is really, what do we actually mean with stability? And that's the last slide that I showed you yesterday. Remember, we had this bowl, and we had a little ball inside, and then the question was, is this ball in an equilibrium situation or not? So would it change its position if we start to apply a small perturbation? And I guess the idea is clear that in this case, the ball would always, if we kind of deflect it a little bit, it would always go back to this what we call equilibrium position. So this situation here, we would call to be stable. And then, of course, the other two situations that we also looked at was this one here or this one. If we have this situation and this situation, in this case, of course, the ball would go down, and this would be an unstable situation, and this one just between the two would be a neutrally stable position. I guess there's not. That's quite obvious. And then the last thing that we also have was this wavy wall. When we said that we have a ball here, that means that initially it would be actually stable, but as soon as we apply too much of a disturbance, then it could actually be that the ball would go over and then suddenly be in another equilibrium situation. And this was the case for conditionally stable environment. So that's, I guess, really the basic idea of stability. And well, if I just summarize that, the question is, what happens if I have a small perturbation? Would it go back to the original position? Then it would be stable. Or if it would go away, it would be unstable. That's essentially. So what we now need to do is we need to find mathematical tools that can actually tell us whether or not we are in a stable or unstable situation based on the underlying equations or perhaps the underlying flow state. Of course, in this case with the bowl and the hill, it's kind of clear. But now we would like to apply the same idea, but on a flow case. So that means we will start with a very simple example, and that is the example of a nonlinear dynamical system. Dynamical system. So how does a nonlinear dynamical system look like? Well, the easiest way to just write that is dq dt is some f, which depends on the state q, and some perturbation or bifurcation parameter, which I can call the Reynolds number in my case. So the q here would be my, what in dynamical system theory, this is typical the state, or the state vector. So that just describes how my system looks like. So that could be the velocities, for instance. So my velocity field could be the state of the system at a specific point in time. This is typically a vector, as our velocity field can be a vector field. It can be at various positions in space. It can have various components, u, v, and w, for instance. But as I said, it's important that this, of course, is a time-dependent, state. As I said, this would be the velocity. The Reynolds number in this here would be my parameter, which I would like to explore to find out whether my system is stable or not, depending on that parameter. So thinking back of the pipe flow that we looked at the video yesterday, we realized, Reynolds made this experiment, and he realized for low Reynolds numbers, the flow was stable. So there was this constant stream of dye. And at some point when the Reynolds number was increased beyond a certain threshold, he discovered that there was this sinuous oscillation in the flow. So the Reynolds number here would take the function of a bifurcation parameter, which would tell us under a certain threshold it's stable, and above it would be unstable. So that's kind of the idea behind this. So what we can also define here is what we can call a base flow or a base state. And that would be the situation when this f of this base state, which I can call QB, and a certain Reynolds number is 0. So that means that there will be no, so in the base state, there will be no temporal change of the state anymore. So that's why it's also called base flow, because it just says that dq dt is actually 0 in this base state. And this we can also say that if we are in this, at a specific Reynolds number in this base state QB, we would be in equilibrium. Of course, that would now kind of mean this point here in the ball. So I just repeat now again what I would now say is the important question. So if you have in here now our bifurcation parameter varying, I would like to go from from a stable situation to an unstable situation as a function of this change in bifurcation parameter. Now it actually turns out that it's maybe not so easy to actually just go from stable to unstable. There may be kind of different parts here on the way. And actually there's, in traditional stability analysis, there's essentially two different critical Reynolds numbers that you have here on this way. We have one Reynolds number here, which we usually call it Re C for the critical Reynolds number, and that would be the Reynolds number that defines you above which everything is unstable. So everything would grow. And therefore, we also write here an additional word, which is unconditionally unstable. This intermediate region here between what I would also call unconditionally stable is, of course, something that is conditionally stable. And that, of course, is exactly what we had in this situation when we had waves or a wavy wall where the waves were, the walls were not infinitely high, so that with a certain specific initial condition, you actually can become unstable, but for other initial conditions or other forces that you would apply to this sphere, it would actually be stable. That's why condition is stable. And that's exactly this intermediate region. And the critical Reynolds number that determines whether you are unconditionally stable or conditionally stable is typically called Re G. Don't ask me what the G, why it's called G, but that's the typical thing that's used. So if I just write that these various conditions down, so we have if the Reynolds number is lower than rate G, that would mean that whatever shape and amplitude I have, no. So whatever shape and amplitude I have of my perturbation, the response of the system decays and goes back to my base state or my equilibrium state QB that I have introduced. So that is if my Reynolds number is lower than rate G. Whatever I do, I will go back to my equilibrium state. And of course, that's exactly this situation. On the other hand, if I somewhere in between rate G and rate C, then it's a bit different. Then the stability depends on shape and amplitude. Of the perturbation. And then, of course, the third case, if the Reynolds number is larger than rate C, then we are in the situation that the stability is lost. Even for infinitesimal disturbances. Of course, that means that even if I just perturb a little bit in any of the directions, it would just exponentially grow and be unstable. And of course, the classical example, of course, is this guy. No matter how, even if I just perturb it a little bit, it will directly be unstable. So what we're now going to do mathematically, or what one is typically doing in stability theory, so stability theory is all about characterizing characterizing the perturbations and studying the development or their development. And that's what we would like to do now. Now, of course, it's always good to have a small example that essentially shows you what is meant with this. And we do now a simple analytical example. But I would like to highlight that everything we do later on with the Navier-Stokes equations is actually just the same methods applied to not just 1 or 2 degrees of freedom, but just to many degrees of freedom. So my simple example would be dq dt, as my dynamical system, is q squared minus aq. So that means I have now a specific choice of this f that I have up here, and my kind of Reynolds number or my bifurcation parameter would now be this a perhaps. So So this is now my dynamical system, and then of course Q here would be a nonlinear quantity. And of course it's nonlinear because we have here a Q square inside. So what do we do? The first thing is to calculate the base state of this system. And of course, how to calculate base states? Well, we need to somehow find the equilibrium, which is defined as dq dt being 0. And of course, in this case, this just means that q squared minus aq would be 0, and this we can factorize quite easily. It's q times q minus a. And of course, with this, we can then see that my two base states are either when q is 0 or q minus a is 0. So qb is either 0 or a. So these are my two base states of the system. So that means our stability will, of course, depend on which one of these base states I'm going to look at. The second step that we always do in a stability analysis is that we need to realize that the important thing is the region just close to this to the base states. So that means a linearization is typically what we can do, because we're only interested in the region very close to either, in this case, QB being 0 or Q being A. So we do a linearization about the base states, and in this case it would be QB being either 0 or A. So we do a linearization about QB, and of course how do we do that? Well, the idea is that we say that our nonlinear quantity Q would be this QB plus a disturbance around QB. The disturbance here, I write with a Q and a tilde on top. And of course, that means if I just fill that into my dynamical system that I have here, so my dq dt would then be a dqb dt plus dq tilde dt. That's on the left side. And on the right side, I have my qb plus q tilde squared minus a times qb plus q tilde. So this now at this point is not yet linearized. I'm just putting in the decomposition in, but of course now I can see that and of course this guy would be 0, because we assume that we look at the stability about a steady base state. So therefore, dqb dt would of course be 0. At the same time, we know that the base state is actually fulfilling the right-hand side. So that means that well, I guess I need to do one more step here. I need to evaluate this. Evaluate this square here to be qb squared plus 2 qb q tilde plus q tilde squared, and then I have minus a times qb minus a times q tilde. So I know that the right-hand side is actually fulfilled, so that means that this term together with this term would go away, because I know that I'm actually looking at so I know that qb squared minus a qb is 0 because it fulfills the base. And then in terms of doing actually a linearization, it means that, well, this guy, so this term here, q tilde squared, would go away. So this is the step of a linearization where I assume that q tilde is much smaller than qb. So that means, well, I can write it. So this means that q tilde squared is of course much smaller than q tilde, much smaller than q. So therefore I can get rid of this term. And of course the beauty now is that I realized that I have actually found a much simpler equation for the evolution of my perturbation. So if I collect everything that remains, so I have this guy left, and I have this and this term left, it means that my evolution equation would be dq tilde dt, which is 2qb q tilde minus a q tilde. So this is what is left. And of course, I can realize that this is now a linear equation, because the nonlinearity obviously has gone away with the linearization, which I can just write as some operator j times q tilde. And this operator j is of course nothing else than 2qb minus a. And I guess you know why this is a j. This j is typically called the Jacobian of my system. So the Jacobian is the kind of the operator that remains if you perform the linearization. So what I have now obtained is a linear equation. Linear equation for the evolution of q tilde, so my perturbation. And of course now the stability problem has been transformed into the problem of actually identifying whether q tilde, so the disturbance to the base flow, whether this perturbation would actually grow in time or it would decay in time. So that's now our stability problem. So that means the third step in our kind of analysis would be to actually perform or do a solution of this linearized equation. So we try to calculate a solution to what equation star, if I call this to be equation star. And of course now it's a linear ordinary differential equation. So q tilde is, well, the solution of this equation can actually be written quite nicely, or in closed form. We have dq dt is j times q. J is constant. Well, what do we get? It's actually just an exponential, as simple as that. So in this case, it would be e to the 2qb minus a times t times some initial condition q tilde 0. Right? So the exponent here is exactly our Jacobian of the system. Maybe I can write that here. So the j here is actually 2qb minus a. So the exponent is just the Jacobian. So e to the jt times the initial condition. And of course now it becomes kind of easy to determine whether we have something growing or we have something decaying. Because the only thing that we need to do is we need to look at the sign of the j. If j is larger than 0, we will have exponential growth in time. If j is lower than 0, we will have exponential decay as a function of time. So the stability problem has now become analyzing the sign of j. And of course now for our little case here, for this example, we actually had two different QBs. We had 0 and a as the two equilibrium points of the problem. So of course now we need to analyze those separately. So we have the first base state, which was QB being 0. And there we can now write down the solution. Q tilde is e to the minus AT. So if I put in QB here, so I just get minus AT, Q tilde 0. And of course this now, because I mean, if A is positive, then this would correspond to a stable situation, because my perturbation would actually decay as a function of time. So this would now would mean that Q tilde would actually go to 0 for t going to infinity. Actually, I haven't stated here, I think, but let's write down that A is larger than 0. So just this. So that means this would be a stable fixed point or a stable equilibrium point in QB being 0. Now, if we look at the other situation, when we had as the equilibrium point, the point at A, then of course my Q tilde would be e to the, well, now we have 2A minus A. So that means e to the plus AT, Q tilde, 0. And of course, now with what we have seen here, this Q tilde would now go to infinity for t going to infinity, just because we have exponential growth as a function of time. And of course, this now would be an unstable situation. So essentially now we have already determined the stability of our problem. We just looked at the sign of our Jacobian. If it's positive, it will grow. If it's negative, it will decay. Maybe as a fourth step, it's not really a step here, but just as an additional way of looking at that in kind of more detail, the idea would be we can actually look at this in complex space. So we can work in complex space, or if you wish, we can look at that in frequency domain. So the idea would just be to kind of say that our disturbance Q tilde can be written as the real part of Q hat times e to the I lambda t. So this is a typical way that I guess you have done before as well, and we have done together for the problem of Stokes, for the second Stokes problem, where essentially, because we would like to look at something that both has a kind of a harmonic dependence in time, but also may have a superimposed growth or decay, as we have seen here. So therefore, we can write this as a complex exponential, and then of course our real solution would just be the real part of this complex exponential. Of course, this real part can also be written in the way that this is just 1/2 of Q hat 0 times e to the lambda t plus the complex conjugate. And that's just a definition of extracting the real part of a complex number. So it's a sum of the complex number plus its complex conjugate. Okay, I guess that's a good time to take a break. And yeah, so we continue in 15 minutes. When we would then analyze a little bit more how this way of actually writing everything in complex space would give us, a better way of identifying exactly these stable and unstable fixed points. But then let's take now 15 minutes break.